Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Quick note before we begin, the Finding Genius Foundation, as part of the Finding Genius Podcast, has recently completed a book about understanding viruses. So the creation of this book was to interview 100 virologists, ask them a lot of deep, difficult questions, take the most difficult questions, and then re-interview the top 25 or so and ask them the hardest questions I could think of. And we compiled that all into a book. So you'll see question and 4 or 5 experts' answers. Question, 4 or 5 experts' answers. There's about 30 questions in the book. I think it's a great read for the layperson and for the researcher. It talks about a lot of speculation in the world of viruses, such as are they alive or not, and why is it important? Why do viruses go latent or hidden or ineffective or sit in a person or an animal or another creature for weeks, months, years, and then suddenly become virulent and affect that person? So there's a lot of really provocative questions in the book. It's now on Amazon. So if you go to Amazon and type in Finding Genius, you'll see the book on viruses. It's also on Kindle. The Audible version is in production and should be ready in approximately a month. But if you want to go and order it now, you can do so again by going to Amazon or Kindle, or go to findinggeniusfoundation.org and go to publications. There's an opportunity as well to get the transcripts of all the interviews and to hear the original interviews themselves. If we put them all together, the book would be about 1,000 pages, but we condensed them down to make it juicy and concise and tight and very interesting. So I hope you'll check out the book. We're now working on one about cancer, but this is going to be our goal is 3 times a year to come out with these masterclass books that I think will inspire new scientific research, and I hope you'll check it out. Thank you. Hello, this is Richard Jacobs with the Finding Genius Podcast, now a part of the Finding Genius Foundation. A quick word from our sponsor, benefactor here. Finding Genius Foundation has recently come out with a book called Understanding Viruses. It's a compilation of interviews with 25 top virologists. It's on Amazon. You go to Amazon and type Finding Genius. You'll see the book, and it's available for purchase on Amazon and Kindle, and the Audible version is coming soon. Today, my guest is Brendon Coventry. He's an associate professor of surgery in Adelaide in South Australia. And we're going to talk about melanoma, breast cancer, and surgical oncology, and possibility of a vaccine, I believe, for melanoma. So, Brendon, thank you for coming.
Thank you very much, Richard.
Yeah. Well, tell me about your work. Is it mostly clinical in surgery, or is it also research? What's the split for you?
It's a little bit of both. It's translational. It's going backwards and forwards between the surgery, the clinic, and the lab, and at the same time trying to assimilate a lot of the literature that's going on around us. So it's truly translational, and it's probably one of the hardest areas that a researcher can do, because and I think any true translational researcher will say that, because it's just incredibly difficult. You're working in universes that kind of only appreciate their own universe, if you know what I mean, and so the clinical people sort of think of you as a bit of a half-baked clinician, and the researchers think of you as a bit of a half-baked researcher. And the problem is that trying to sort of straddle this bridge, if you like, is incredibly difficult, and it's administratively difficult. Like, the administrators don't seem to really appreciate the true worth of translational research, and also in terms of trying to get funding and things. I mean, you would think that would be where the funding would be thrown, but ironically, a lot of the funding is directed at either sort of pure clinical research or pure fundamental research, and where you truly try to cross a bridge, particularly if it's not a particularly popular area at the time, it becomes incredibly difficult. And so, if there's any people that control money and funding that are listening, really and truly, this is where the money should be being put, or a whole lot more should be put, because it's not to say pure clinical and pure fundamental research aren't vitally important, but I think the true translational bridge work, which is so damn difficult, is not really terribly well funded. It's really, really hard to get money.
Yeah, I thought that there's an SBIR program and an STTR program through NIH for translational work.
Yeah. So there's the R21 schemes and various other schemes that are really good, but you know they're not that open to people from outside the US. I think it's going to get pretty interesting with COVID and a lot of the additional research that's gone on. But you know, some of this might help us too. I've been musing lately about how COVID might actually help a lot of other research, like cancer research. For example, we've never really looked terribly much. It's never been popular to look at the common cold. Now, some 20 to 30% of common cold viruses are coronaviruses. So this is getting really interesting. I mean, now for once we've had tons of money thrown and lots of research time thrown at the coronavirus. And so, you know, we may get to understand a lot about the way the common cold works, which could lead us to some fundamental understanding about how the immune system works, you know, how we defend ourselves and so on. And that will lead to understanding about cancer, I believe, too.
Well, tell me about your research. Let's focus on that. What's that look like?
Yeah, so we, I sort of got interested in the immune system many years ago at high school, and I was looking at snails taking up carbon particles and phagocytosing them. And you could see all this in real time. It was truly fascinating for a young person coming into the whole area of immunology. And about that time, you know, a bit before maybe McFarlane Burnett was publishing with Medawar, publishing articles on trying to control viruses using interferon. And it was also noticed at that time that you could control some cancers with these similar sort of cytokines. He coined the immunosurveillance hypothesis for cancer, saying that, you know, the immune system in people and animals was pretty highly tuned to picking up aberrant, malignant, so-called cancer-type cells, and that these were removed from the system. So it was only the ones that sort of escaped immunosurveillance that ended up with cancer, as we know it clinically. I thought that was fascinating, and I still think it's fascinating, and I'm still fascinated probably just as much, if not more, today as I was then. This led me to do a PhD in tumour-infiltrating lymphocytes, which was starting to get popular in the early 80s, and then ultimately became really interesting in the late 80s. A lot of work out of the NIH with Steve Rosenberg and many others that were looking at that. And about that time, I had the opportunity to get involved in a vaccine trial that was going on in Australia using a type of vaccine that came from a patient's melanoma cells, and it was able to cause a lot of reactivity in a lot of other patients. So it was really quite interesting. And then I got involved in some NIH trials that were sort of multi-centre, and some of the centres in Australia participated in those, and that was fascinating too. So I started looking at different types of cancer vaccines, and ultimately, you know, it became more and more interesting that the purer you made the vaccine, the less effective it was. So we sort of, I particularly, but our group and others started focusing on the sort of more complex vaccines, the ones that in many respects were so, for want of a better word, dirty vaccines. They weren't clean at all. They weren't like a drug where you could synthesize, say, a single molecule. They actually were complex, and they had lots of componentry to them. And it was like the immune system was somehow being sort of more broadly primed, and that somehow made it much more likely to get an effective response. And so in about 2000, we'd finished one trial, and the vaccine, and in fact, the trial itself was done in sort of slightly earlier stage melanoma, and it was effectively a negative result. But interestingly, the curve for the treated group compared to the placebo group was always greater. And I thought that was fascinating. It was on the verge of being statistically significant, but not quite. And I just kind of thought that something was sitting behind there, but I couldn't make it out, and neither could anyone else. And you know, it was largely scrap-heaped as a vaccine. And in about 2000, a chap was sent to me by another surgeon, and this chap had multiple melanomas removed, and it was getting to the stage where after, some 20-odd operations removing small deposits and having had radiation treatment and various other things for deeper melanoma in his body.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
The surgeon said, look, every time he's coming back to have his sutures out, there's more that are popping up. Is there anything you could offer him immunotherapeutically? And I looked at we were just about to start one trial, an NIH trial, and we'd finished this other trial that I'd mentioned, and I said to him, look, I don't know, but I said there's chemotherapy, which has a very, very low response rate. It's maybe 10% response rate and about a 1% survival for advanced melanoma. So it was pretty hopeless, and the side effects were present too in a large number of patients. So I said, well, look, there's this vaccine that we have trialed and we have a lot of experience with. We know it's not toxic. We know that it really doesn't seem to affect people apart from having some effect against the tumor, but we can't.
What was the vaccine for? Is this off use, or was it made for melanoma?
Yeah, well, it was an experimental vaccine, a lysate, what we call a lysate vaccine, which is it's manufactured by lysing existing cancer cells that are set up in a cancer cell line, so it's grown and replicating line, and we lyse it. And interestingly, we have lysed it. This particular vaccine, we lysed with a virus, and it was an oncolytic virus, a very well-established virus, a vaccinia virus, and that was, of course, used in the smallpox epidemic to try and vaccinate against smallpox. But it also selectively bursts cancer cells, and we don't know why, but it is quite active against cancer cells. There's a number of viruses that are oncolytic and like that, and so it was the vaccine product was a lysate. It comprised of tiny fragments of viral particles, but lots of debris from cells that have been burst, and so very what you might call an impure vaccine, a so-called dirty vaccine. And
well, I thought the stuff they add to it, they call adjuvants, I guess, to stimulate the immune system to have a larger reaction than it otherwise would.
Yeah, that's right. And so there's been a lot of work with adjuvants, but adjuvants are an addition. They're an
right.
Addition
they're not the main
to the vaccine
mechanism.
No, adjuvants represent something that you're adding to the vaccine to make it stronger, make the response stronger, and so this probably had its own adjuvant in there. It probably had mechanisms for boosting the reaction that you would have got if you'd not had, say, viral particles in there. I think this is turning out to be incredibly important, and we're noticing it with a lot of research. Some of the coronavirus stuff's looking interesting in that area too. But the nuts and bolts of the story and the beginning really came in 2000 when this chap came along, and we just couldn't stop his tumor. The surgery was not being effective. So I said to him, look, there is this vaccine, we could try that. I said it's probably worth a go, but I can't guarantee it will do anything. Anyway, he had one dose and came back, and he said, look, doc, he said, I think it's starting to disappear. And I said, really? I said, no, this is pretty interesting. So I had a look, and sure enough, it was quite red and inflamed, and it looked like it was decreasing in size, these nodules that you could feel underneath the skin. And anyway, what happened next was I revaccinated him 2 weeks later, and then at this clinic interview, and And then he came back another 2 weeks later for his next vaccine. And he said, look, Doc, they're gone.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
And I said, really? I said, show me. And I had a look, and sure enough, there was nothing to feel anywhere. We performed CTs, and all the tumour that was related to his lung and everything had gone, completely gone. I saw him 2 months ago, and he's now just passed his 20th anniversary of survival from advanced melanoma.
That's wow, that's rare.
Yeah, it is. It's very rare, and I'm really, really enthralled that I could actually witness this. It's an amazing thing when you witness it. And so I don't think if the response had been so dramatic that I would have really gone on to the next patient. And so we've now had a string of patients. I ended up doing a small trial of 50, just over 50 patients, and interestingly, we have had regression in a surprising number. So we had a 17% complete response rate where everything just disappeared. And a lot of people, when I have mentioned this at conferences and things, just they don't believe it. They don't believe that it could happen. And I might have been one of those too if I hadn't seen it myself. But interestingly, this regression is remarkable. And just like was noticed when the vaccine was initially selected, the cell line was selected, it's able to cause responses in a large, wide range of patients. This is interesting in itself. So we're at present trying to sort of unpick this. We've got a lot of blood stored for these patients, and we're trying to sort of unpick all of this. But what we do know is that the actual technology behind this has really never been looked at properly. And we are now trying to unpick it. We've been to probably 5 or 10 pharmaceutical companies, and no one wants to look at it because it's not a simple drug that can be synthesized. But this technology has the opportunity to revolutionize cancer therapy. It's almost certain that most treatments vaccinate patients against their own tumour. And I'll explain this a bit more. It's really interesting. I wrote an article in 2019, and I entitled it Therapeutic Vaccination Immunomodulation, forming the basis of all cancer immunotherapy. And I put a question mark at the end. So was it forming the basis of all cancer immunotherapy, this therapeutic vaccination that's going on? And by the time I'd finished writing the article, I removed the question mark, because in my mind, there was absolutely no doubt that vaccination was occurring with every type of cancer treatment. I think almost every type of cancer treatment.
What does that mean, vaccination is occurring with cancer treatment? What do you mean?
Yeah, exactly. And so, exactly. And
I mean, are people being vaccinated when they have cancer, or what do you mean? You mean chemo and radiation and surgery is vaccinated? I don't understand.
Yeah, the whole lot. How I'll explain it is that we had a lysolytic type vaccine. So we've got a vaccine that comprises a cancer cell line that's been burst apart, and that itself is able to induce complete responses. We've shown that, we've published on that, and we're now sort of looking at any partners that can help us to try and commercialize it. But what we really want to do is drill down a bit more and look at the mechanisms that are going on here. So we had a lysae, burst cancer cells, that could actually engineer an immune response. Now, when I started to think about this, I thought, well, what does chemotherapy do? What does surgery do? What does radiation treatment do? What does, in fact, immunotherapy itself do? Well, what it does is all of these treatments are able to induce a certain small rate of complete response where all the tumour disappears. Fascinating. How can multiple different mechanisms that are said to be working through entirely different pathways, how can they actually engineer complete responses, which is the final common denominator? So I started thinking about this, and I thought, well, just imagine for a minute that if all of these treatments at a small rate were able to damage cancer cells to such a degree that they could cause a lysae, a bit like our vaccine, and they could then release antigen from the cancer cells, then that could get into the patient's circulation and tissues, and it could incite an immune response. So it may be, and it's almost certainly true, I believe, that the immune response that is occurring to a lot of these treatments, including surgery, is absolutely instrumental in the patient actually trying to treat their own cancer. So in other words, the treatment is really just the mechanism for disturbing the cancer microenvironment to such a degree that antigen gets released, and then that antigen itself is able to incite an immune response in the patient.
So chemotherapy, I mean, it's systemic. It's killing fast-growing cells, supposedly. But are you saying that's not its only method? It's also stimulating those cells to release antigen so the immune system will be more likely to pick them up?
Yeah, and that question is really important, because what it shows is the, I guess in a way, that the sort of difference in understanding that we've had, where imagine a chemotherapeutic agent, it's said to be cytotoxic, it's said to actually just kill a cancer cell. So we're thinking of cancer as being a massive dividing cells that are killed by the chemotherapy agent, and that the death of the cells means that they're taken out of the equation, and that it's this depletion of cancer cells that's leading to the recovery of the patient. And that may well be true. But what's happening at the same time is there's death of cancer cells. And that as the cancer cells die, the cancer cells release all of the surface molecules and the contents of the cells. They burst. And in that process is released a whole lot of chemicals that are contained on the melanoma or the cancer. And this goes for I believe much wider than melanoma. It's all cancers. The surface of the cancer cell contains these antigens. These antigens can be recognised by the immune system. They maybe not are able to be recognised as clearly or as strongly as is needed to get rid of them naturally by the patient's own immune mechanisms. But what happens is that this release of antigen is enough to incite the immune response and switch it on. And it may be that it needs some other triggers too, like danger signals that come from viral pathogens or bacterial pathogens. And it may be why we get responses to certain infections, and these were described way back 100, 150 years ago, that certain infections occurring at the time that a patient has a cancer can lead to spontaneous regression.
So ideally, you'd be able to replace chemoradiation and surgery with, a vaccine type element that would stimulate the immune system in a similar way, but you wouldn't have to do any of these other treatments, which are invasive and destructive.
Yeah, it might be. It might be that we supply the vaccine like we're doing currently in our studies, that we actually inject the vaccine and we inject it intradermally so that it gets taken up by special cells in the skin that can present antigen better, called dendritic cells. And it may be that we actually supply exogenous vaccine, or it may be that we find ways of actually selectively destroying cancer cells in the patient so that we can incite the immune reaction that's going on. Because after all, what's happening in the patient when a cancer is growing is there's a certain death rate in that cancer mass. And so as the death rate is going on, the immune system is constantly being primed. It's constantly being exposed to the antigen from the cells that are dying. And in this process, the immune system's being stimulated at intervals. And it looks like the immune system's being stimulated in waves almost. We noticed this with some of our vaccine patients, and we searched a little harder, and we looked at the way that the immune system was being switched on and switched off. We monitored patients using CRP, a very general marker for inflammation that we use a lot in surgery for a lot of things like appendicitis and pancreatitis and various other infections. So we used CRP, and what we noticed was that if we did it on a near daily basis, we could see fluctuations in the CRP level. We thought we used some really simple mathematics, and it turned out that they were too simple. And we looked at the fluctuation thinking that it was probably quite regular, but there's a lot of noise going on here. And we've now used some artificial intelligence to try and drill down a little further, and used deep learning to try and look at this a bit better to see if we can predict when it might be better to treat, for example, as opposed to not treat. I mean, we know that that a lot of vaccination that occurs to infectious disease might be dependent on the time of day that the vaccine's given. So there's a lot of sort of diurnal rhythms and other aspects of cancer treatment that are essentially unexplored, almost completely unexplored. And we were starting to drill down here with some of our vaccine work as well.
Well, are you repurposing existing vaccines, or do you now have any hints on new vaccines to create? Or, are you looking at technology that appears to be, again, oncolytic, and then pairing it with adjuvants to make it into vaccine-like treatment? Like, what's the first path forward, or do you have to go through all paths?
All of the above. We're sort of, at the moment, we're looking at trying to understand why the vaccine that we've got works. If we can understand that, we might be able to engineer some better responses. It's possible that we could, and a lot of it's been revolving around toxicity too, because one of the key problems with the current newer immunotherapies that have come out, which have been massively helpful to our cause, because until very recently, we've been told by many people, including a lot of clinical oncologists, that the immune system's got nothing to do with cancer. It's almost unbelievable now with what we know with the anti-PD-1 treatments and the anti-CTLA-4 treatments. But when you just go back a few short years, 10 years or so, the only real immunotherapy that we had was interleukin-2 and perhaps BCG, tuberculosis vaccine, which was used for bladder cancer, and it was used for melanoma as well. And no one really believed that vaccination could work. It had a very checkered history, and if you go back in the literature, a lot of the studies were negative. So there was a lot of skepticism about the immune system and cancer, and a lot of skepticism about vaccines, and I think there's still a bit of that hanging over. But when the anti-PD-1 and anti-CTLA-4 immunotherapies came along, suddenly we started to see much better responses to, say, conditions like advanced melanoma and then lung cancer and quite a number of other cancers now. But not only did we see that, but we saw rampant autoimmunity being unleashed. And one of the interesting, most fascinating things about all of this is that the autoimmunity almost parallels the response, the clinical response against the cancer. So
what does that mean, it parallels the clinical response?
Well, what happens is that when a patient has a response in their cancer to the immunotherapy, they almost always have autoimmunity as a side effect. In other words, what it's doing is it's somehow unleashing the control over tolerance, really. It's reducing the tolerance that the immune system has to a lot of normal tissue. So it's not uncommon to get pneumonitis or colitis or affect the pituitary or the thyroid. It's fascinating that autoimmunity is almost necessary for the effectiveness of these immunotherapies. Now, the immunotherapies, like interleukin-2, anti-CTLA-4 and anti-PD-1, they all effectively are pure immune drivers. They just drive the existing immune response on. And so that means that if we're getting responses when we just simply push the accelerator down, then we must be pointing in the right direction for a certain number of patients, and therefore just accelerate what must be a slightly ineffective immune response going on underneath against their own cancer.
Yeah, would you think it's ineffective, or would you think it's overdone? I mean, it seems to, to take on a life of its own and do too much. And that's the autoimmune, that's the characterization of the autoimmune response.
No, you're quite right. It's the alternative hypothesis, and it has been that sort of concept has been proposed by quite a number of people, that in fact we're just sort of, the wheels are spinning, if you like. It's not so much a problem with engaging and getting traction. It's actually that the wheels have been lifted up, and you can't so the engine's on, the wheels are spinning, but we're not actually moving anywhere. And you're stating, well, look, it's overdone. Well, yes, it could be. We're not really sure which way around it is, whether it's a situation where the wheels are spinning and these treatments just put the vehicle down and allow it to go, or whether in fact it's happening at such an ineffective level that just a little bit of a boost over the top actually engineers a correct immune response that is.
Well, why don't you try to find a sweet spot and tone down the adjuvant to the minimum level, and thereby you might reduce the autoimmune response later.
Yeah, and people have done that. They've turned back the amount of IL-2, anti-CTLA-4. That people have tried it in all sorts of dose levels, and what is found is that in general, if you turn it back so you're not inducing autoimmunity, it doesn't seem to have as much effect clinically. It's not as it's not got as greater effectiveness. So this is all fascinating. We're learning a lot. We're not sort of in an area at the moment where we can engineer responses as effectively as we'd like and to minimise toxicity as effectively as we like. But it's gaining a lot of ground. We also know that the microbiome is important. There's been a number of studies that have demonstrated that by modifying the microbiome, that's the gut bacteria basically, then you can alter the effectiveness of some of these immunotherapies. So there's some things going on in the background that we don't quite comprehend yet, but we're gradually unpicking it.
Well, yeah, very good, Brendon. Unfortunately, today we're out of time, but it definitely sounds like we need to have another conversation about this in the future if you're willing. But where can people find out more about your work at this moment? Where can they go?
Well, we've got a number of publications. There's basically just Google Scholar, and that should be able to pick up some of the publications that we've been putting out. And you can Google vaccine treatment of melanoma, and that should give some results as well. I'm happy for people to contact me directly if they'd like.
Okay, very good. Well, Brendon, thank you for coming and talking about this. And again, it's like we just touched the tip of the iceberg. So
my pleasure, Richard. Yes, indeed. We're right on the cusp, and I think this is going to be a very fascinating journey in the next 10 years or so.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.